On behalf of ATAL FDP organizing team of PCCOE Pune, I extend a warm welcome to all the attendees for today's insightful sessions. We have two enriching sessions lined up for today, which are on powering the electric vehicles. The first session, that is powering electric vehicles, exploring energy sources, will be delivered by our beloved Dr. Deepak Vatvisave, who is working as an associate professor at Cummins College of Engineering for Women, Pune. Dr. Deepak holds a PhD from IIT Bombay. He did his graduation and post-graduation from College of Engineering, Pune. With an impressive 29 years of experience in industry, research, and academia, his expertise include machine learning, artificial intelligence, electric vehicle technology, C++, CFD, CAE, and molecular dynamics. He has successfully completed numerous industry-sponsored projects and guided many UG and PG students in their academic pursuits. Additionally, Deepak sir has published over 12 research articles and received DST funding of 32 lakh rupees for the project named Smart Water Conservation System. So, today we are delighted to have such a distinguished expert with us. Thus, I appeal the attendees to participate actively and make most of this session. Thank you, and I wish you an engaging and fruitful learning experience from Deepak sir. Over to you, Deepak sir.
Thank you, Varsha madam. First of all, I would like to thank the organizers of this workshop, all the faculty members, mechanical department of Pimpri Chinchwad College of Engineering, Pune. It is very nice that you have given me opportunity to share whatever knowledge I have about the modeling of lithium-ion battery. I also take opportunity to welcome the participants from colleges, the industries all over India. Okay, so thank you. So let me share my presentation. I hope that I will finish my presentation within 90 minutes, and for 15 minutes there will be question and answer session. Okay, so let me share my screen. I hope my screen is visible to all of you participants.
Yes, sir, it is visible.
Yes, sir, yes.
Okay, pardon. Okay, so shall I start?
Yes, sir, we are good to go.
Okay, so the topic given to me was is powering electric vehicles, exploring energy sources. Actually, I have had a lot of chances to put into here when we are exploring energy sources. Like I could have discussed about modeling of hydrogen fuel cells. I could have talked here about then hybrid energy system and about technology and showing you some fancy colors and all those things. Actually, I have avoided all those things, and I would like to explore energy sources, mainly lithium-ion battery, through fundamental perspectives on battery modeling. Because most of here we are faculty members who are guiding to MTech students and also PhD students, and still I think that still open or complex problems are still there in battery modeling, which we can address if we know or if we concentrate on fundamentals. Because see, I'm from academia, and many other speakers are there who are from industry. So I think that the people who are from industry, they should talk about whatever current things are there, what are current technologies they are working on, what are current developments those people are doing. And we, the academicians or teachers, should talk about mathematics and underlying physics. So that is my aim. So accordingly, the title of my presentation is Powering Electric Vehicles, Exploring Energy Sources Through Fundamentals Perspectives on Battery Modeling. And mainly here, I would be talking about the complete overview of equivalent circuit models, and even I will be sharing with you, or I will be discussing a ready-made example available on MATLAB, so that at least whatever takeaway is there from today's lecture will be, at least we will be downloading your data and we will be doing some simulation with some understanding. Okay, So that should be the outcome of this 1 hour or 1.5 hour interaction. So let me start it. Again, the contents are lithium-ion battery working. Actually, I'm assuming that all of you are knowing it, lithium-ion battery working. So I'll not be taking much time on it. Then thermal issues. Then some time will be spending on MSMT modeling. Then we'll see a very simple model or slightly complicated model, Newman pseudo two-dimensional model, NTGK model, ECM model, and my main focus is on ECM model and its implementation in MATLAB, so that it will be really useful to all of us, because I think that I'm also currently working on few problems where I'm using this ECM model for different problems. Like for example, you can take hybrid energy storage system, consisting of lithium-ion battery, then supercapacitor. Then can combine together, and they can instead of working at very actually at a micro scale or a nano scale, we can work at macro level. Okay, so mainly I will be talking about ECM model and the MATLAB ECM parameter estimation example. Okay, so before that, see, the main topic is, if you really want to understand what exactly is MSD modeling, we really have to work at various levels. So many domains are there and so many scales are there. And instead of describing how battery works, because I'm assuming that all of you know it, so this is equation for, this is a chemical reaction for discharging. This is chemical reaction or electrochemical reaction for charging. And if you look at, see here, at the electrode level, the ions are separated from lithium. So this separation or this electrochemical reaction, the scale of this chemical reaction is at atomic scale. So if you really want to understand what exactly is happening from physics point of view, you have to think at atomic level. Then if you see the separator, the separator is scale. Separator is scale. If you see the total scale of the battery, it is centimeter scale. Okay, so we are moving, see, atomic scale is Armstrong scale. So from Armstrong scale, we can come to scale, then from to centimeter. Okay, so these scales are involved. So the battery modeling is called as multi-scale. Okay, MSMD, multi-scale. Another issue is, now if you look at the materials, so there is lithium metal oxide, then this separator is porous separator, so it is a sort of plastic. Then cathode, anode, they are of different metals. Graphite is there. So these various domains are there, and here I am excluding the load. So if you just look at the battery, so many domains are there. Because of that, if you really want to understand the physics of the battery working from very fundamental level, so many equations will be there, so many things we have to take into account. So battery modeling actually is a multi-scale, multi-domain modeling. Okay, so now taking this as a cue, so I'm not discussing how this battery is working. Now the main aim, so now I'm a mechanical engineer, and I think that most of you are from mechanical engineering. Our main focus is, so when you are working on the battery, one of the major issues is thermal issues. Okay, so if a battery design problem is given to you, battery management problem is given to you, mainly mechanical engineers will be working on, or generally they are working, I'm not saying that you are not working on voltage side or current side or motor side, but main issue to be addressed are the thermal issues. So what are the thermal issues? Again, we know how heat is generated. Now, when thermal issues are there, when the battery is heating up, when the temperature of the battery is rising up, why it is rising? It is rising because of Joule setting. Then there are electrochemical heat generation at the electrodes. This electrochemical heat generation is what? When electrons are separating from a lithium atom and lithium ions are generated. So at that level, that is at micro level, then we know that there is always entropy. We cannot get rid of entropy. So because of entropy, there is heat generation. Then there is heat generated due to short circuit. Then there is thermal abuse or thermal run away due to high temperatures. And our main aim in battery design or battery thermal management is to avoid this. So to avoid this is our main aim. We don't want to enter into this condition. Okay. And we see this thing will be there because the current is passing through the battery. This is joule sitting, so we cannot avoid it. Similarly, electrochemical reaction we cannot avoid, and this entropy is given by us, given to us by nature, so we can also cannot avoid this, but we can avoid this. And also our aim is to avoid, when we are designing battery system, we must think about it. Okay, otherwise there will be thermal runaway, higher temperatures will be there, and it will give rise to battery chemical reaction and disintegration. Again, I will not be discussing thermal issues. I will not be showing you any simulation like ANSYS simulation or fluent simulation. I will be at fundamental level. Okay, so these are the thermal issues. And now I will come to MSMD modeling, some description of MSMD modeling. The multi-scale multi-domain modeling deals with physics at micro scale to battery length scale in different solution domains. The lithium ion transport occurs in the anode separator cathode sandwich layers at the length scale of electrode pair. Lithium ion transport in an active material occurs at the atomic scale, length scale. The solutions domains are, so what are the solution domains? So we have to work at electrode level, then electrolyte is there, separator is there, and current collectors are there. However, okay, so everything is happening. So much of dynamics is happening at so many levels and so many domains. But when we are saying that we are mechanical engineers and we have to design thermal management system. So what exactly we are doing? So, however, the main task is to determine temperature distribution at the battery length scale. So, if somebody gives you, or if you get the temperatures of the battery or the temperature distribution over the length scale of the battery, okay, at least our work is done. We can then design cooling system such that there will not be any thermal runaway. So that is our objective. See, so this is our outcome. But to reach to this outcome, these many stages are there. Atomic scales are there. Then various domains are there. Okay. Again, see, whatever make these scales, whatever make the problem, but governing differential equation, they are not going to change. Okay. So we are doing same thing again and again. We are applying same differential equation. Only the scene is different. So for temperature distribution, unsteady heat conduction equation with internal heat generation is solved at battery scale. So somebody is solving battery thermal management problem using COMSOL or Altair finite element analysis, Altair CFD package or ANSYS Fluent. What they are doing, they are solving this unsteady heat conduction equation with various source terms, and we'll see how those source terms are coming into the differential equation. Again, now since there is coupling between heat generation source terms and electrical field variables. So what are the electrical field variables in battery? Again, voltage and current, potential and current. Then electric field equations are solved. So here, if you really want to solve this temperature distribution problem of the battery, we have to solve these two equations. This electrical field equations involving potential and current coupled with unsteady state heat conduction equation. Shortly, MSMD for CFD analysis of battery is nothing but, see, whatever is happening at the back end of your ANSYS Fluent, whatever is happening at the back end of your COMSOL software. Ultimately, what they are doing, they are solving unsteady state heat conduction equation with source term coupled with this voltage equations. So that's it. And now we are going to see these equations, and then I will bring all of your attention to the equivalent circuit model, which are very, very simple than all this physics level model or physics based model. Okay, so I would like to bring your attention to this equation. So this is energy equation. Everybody of you or everybody of us know this equation. So this is nothing actually new in this, but it is good practice to look at the differential equation once again. Okay, so this energy equation is solved when we are trying to find out what the battery temperature. So this is battery temperature in which we are interested in. I need not discuss this. Okay, so this is unstudied term, then this is diffusion term, then so this is happening. So this is the conductivity, then this is potential. This is potential at the positive electrode. This is potential at the negative electrode, and this is electrochemical heat generation. Then source term because of short circuit of the battery, and this is source term because of the thermal abuse or any abuse of the battery. Okay, and in see now, so this is another differential equation. So this J dot ECH is volumetric current density. So whatever, suppose there is battery, and when you are taking, when current is passing through that battery, okay, now this current is related to this. So we cannot directly correlate this current to this. So we'll see the models how this J dot ECH electrochemical is correlated with whatever current is flowing through the battery at the terminal. Okay, so these two equations are to be solved. But what we want, see, getting Cp rho, actually this is also very difficult in lithium ion battery, because see, if standard materials are there, then rho and Cp, then thermal conductivity, all those values are available. So look at the complexity of this problem. If you really want to know the density, the specific heat, and the conductivity of the lithium ion battery, we should get this data from where? We have to get it from manufacturer. But I don't think that any manufacturer will be interested to share this data to anybody. Okay, so these equations look simple, but getting this data is slightly difficult. Okay, not only that, this is this electric conductivity, this is also electric conductivity at both the electrodes. So getting this data, so what I am saying that, see, we have to get this data, and we have to find out this Q dot ECH. So these are the source terms. Okay, so these are also source terms, but these source terms are coupled to this differential equation. So what is happening at the when we are using this ANSYS fluent? So these equations are discretized. These two equations are discretized. This equation is discretized, and when equations are solved, when solver is solving the equation, for this equation will be solved this phi plus phi minus at all the domains, at the centers of the domains will be put into here, and then this equation will be solved. Okay, so like this, your calculation process or your simulation will go at the back end of ANSYS or COMSOL. Okay, so these two equations are solved. Now we'll see how difficult it is to get these terms. Okay, once you get this, again, this is also source term. So this is also source term. This is also source term. And for the moment, if you don't want to increase the complexity, we'll say, okay, there is no short circuit. Okay, so if short circuit is not there and abyss is not there, then our life is safe. So we have only this. Again, we cannot get rid of this electrochemical heat generation. Electrochemical heat generation is going to be there. Okay, and if you look at carefully at these two terms, so these two terms are what? So thermal conductivity multiplied by voltage. So these are actually Joule heating, or these two terms are equivalent to I square R. See, my point here is that, see, even though this equation looks slightly dangerous, but this is not dangerous, because see, we know Joule heating, we know I square R heating, we know from ages. From 5th standard, we know I square R heating is there. Only thing is that it is written in a different way. But to get this I square R, we have to solve this. Again, this is electrochemical current density. Again, this electrochemical volumetric current density is related to whatever current is flowing through the battery. Okay, so that is also not very difficult. Okay, na? So this is about these two equations which are to be solved when we really want to get temperature distribution of the battery, provided that all the constants are given to you. When I'm saying constant, this rho, k, this sigma plus, sigma minus, and who will be giving you? The manufacturer will be giving you this data, because we are not manufacturing the battery. Okay, so this is about these two equations. Again, I have said that my main focus is on equivalent circuit model, but we'll be discussing it so as to understand how complex these models are there and why people are generally using equivalent circuit model. So this is Newman P2D model. So actually, in reality, what is happening? Everything is three-dimensional. So what we have to do? So if you look at this equation, so this is three-dimensional equation. So what this Newman has done, actually a very nice paper is there written by Newman, and he has explained how he has derived this P2D model. So P2D is not very great thing. So it is actually pseudo 2D model. Okay, so actually it is 2D model. So I'll just read it because the derivation is slightly difficult, and I'm not here to discuss about the derivation. I will just give some overview of this model. So what is happening? How this model is derived? So what Newman said, during the discharge process, lithium ion diffuses to the surface of negative electrode particles, and undergoes an electrochemical reaction. Okay, so it is shown over here, and this is the particle. Okay, so negative electrode particles are idealized like this, two-dimensional particles. So this is two-dimensional, but in reality, this is three-dimensional. Okay, so this is major simplification. And what he is saying, that there is a diffusion process. So this reaction releases an electron and transfers lithium to the electrolyte phase. The lithium ions diffuse and conduct through the electrolyte solution from negative electrode to the positive electrode, where similar reaction happens. So that is okay, perfectly all right. Lithium ion is stored inside the positive electrode particle until the cell later is discharged. So that is also normally known to everybody. So what Newman has given to us, and whatever Newman has given, we have to take it and then we have to discuss on it rather than deriving it and discussing about how this diffusion process is happening. Otherwise, we'll enter into very complicated mathematical exercise that I want to avoid. So just look at this Newman model, and this Newman P2. Why I'm taking these two models? Because this is implemented in ANSYS Fluent. And see, almost 99% colleges have ANSYS Fluent software. And if you open this battery model of ANSYS Fluent, you will see this model is there. Okay, so again, I have written here energy equation. So this is all right. Now, what is the task? The source terms. So what are the source terms? The source terms, electrochemical heat generation, rate per unit volume, and current density are given as follows in P2D model. Okay, so what we want now, see here. So for the moment, we'll just get rid of this. So we will think that, okay, there is no short circuit, there is no thermal abuse condition. So this is equal to 0, this is equal to 0. And now this is Joule setting. And this Joule setting depend upon phi plus and phi minus. Okay, these are the potentials, electrode potentials at positive electrode and electrode potential at negative electrode. Again, so okay, so what we can do, if you really want to solve this equation, so what we would have done, so this is your mesh, CFD mesh here. And here your 5 plus values are there. So 5 plus 1, 5 plus 2. So all these values are there, and you'll find out these values using this differential equation, which actually this is differential equation. But in this differential equation, so this is a constant. So this is a constant. So we can put these values, but this is actually this is a second order partial differential equation. Okay. So we are solving for 5 plus. That means these values at the center of the finite volume. So here I have drawn two-dimensional finite volumes. Okay. Again, there is no short circuit. We are assuming that. So what is remaining here? So what is remaining is the electrochemical current volumetric density or current density. So J dot ECH. Now what Newman has done in this model, actually see, getting this using first principles is very difficult. You people might have heard about this Butler-Warmer equation, all those things. Again, I don't want to go into those details. Okay, so what Newman has given us or how it is implemented in ANSYS. Now this term is written like this, and this is very simple. So this is the current at the positive terminal. This is nominal capacity, reference capacity of the battery, ampere hour, and this is volume of the battery. Okay, so it is easy to get this. So if the battery is there with you, if you know this value, means what I am saying here, if the battery is given to you, so this is positive electrode. If you know IP, current at the positive electrode, boom, you are getting this. Okay, so simple it is. So once you are getting this, just by knowing this or this profile of the current at positive terminal, we will plug in this value in this differential equation. Sigma plus sigma minus are known to you. You get 5 plus. So these values you are getting. Now you put these values over here. Now what is the remaining? Okay, getting 5 plus 5 minus, you are getting this joule setting. Now what is remaining is Q dot electrochemical heat generation. For electrochemical heat generation, already you have found out IP, you know IP, it is given to you. Then 5P, 5 plus and 5 minus distribution, we have calculated over here. Okay. And these are what? These are the length of the positive side, the separator, length of the positive terminal. Okay, so these are the length. And for the moment, we just neglect it. So our life has become very simple.
करेल मी बघा तुम्ही जरा केलं तर फार धन्य.
Okay, okay. So these 5 plus 5 minus values are calculated over here. Now what we can do? Now we are, most of you are might have worked in CFD, finite volume method. So what we can do? So at the same, so what we can find out? Here we can find out T1, T2, T3. So we'll solve this equation and we can get this. So it looks very simple. Okay. But problem here is that to get this, to get all these things, Q dot ECH and J dot ECH, if you look at in ANSYS Fluent, so this is the interface. So if you count, so these many constants we have to plug in so that we'll get this T1, T2. See, finally our objective is what? To get temperature distribution in the battery. We really see this 5 plus and 5 minus, they are internal. To get temperature, we are solving for 5 plus and 5 minus. But to get 5 plus 5 minus and all the source term using P2D model, pseudo 2D model, it is simplification. We are going from 3-dimensional to pseudo 2-dimensional model. And here, why it is pseudo 2-dimensional? Because in reality, your particle will be maybe of this size or any arbitrary size. And here, this new one is assuming that your particle is perfectly circular. Even though this model is simplified, so how many constants are required to be inputted? Around 25. Around 25 parameters we have to plug in. But from where we'll get these parameters? It's very difficult to get in. See, this exercise is given. This as a solved problem. This is as a solved exercise is given in ANSYS Fluent. But we are solving this problem. We have to solve this problem for our battery, na? And we are not manufacturing it. And when we are importing these batteries from China, so which Chinese manufacturer is going to give these constants to you? So though this looks very nice and good, very near to first principles, it is slightly difficult. I'm not saying impossible. If you really want to say, okay, I want to do it, you can get these constants, you can plug in there, and you'll get some accuracy. For example, you get, suppose you say you got accuracy of 98% of your simulation, and suppose another scenario, I'm using ECM model and I'm getting 90% accuracy. Okay, so I will accept this rather than taking so much of effort getting these constants and getting 90% accuracy of your CFD simulation for temperature distribution. I will manage with ECM model, and that is my focus that I am pressing. Okay. You might have done this numeric P2D model. If you are done, you just go and the solve exercises there. You can solve it. Whatever constants are there, you can just see you are getting good results. But only for whatever battery model, whatever battery is specified in the exercise. It is very difficult to claim that whatever input values you are putting, they are corresponding to our battery. So this is, I will say, okay, this is out of question. Okay. Useful to understand how battery works, how things are happening. This model is good, but doing something of our own, it is slightly difficult. Now we'll go to another model. Again, this model is also implemented in ANSYS. Again, this is semi-empirical model. The previous model was classical model. Now this is semi-empirical model. And the beauty of this model is we want only these two constants, U and Y. And all the source terms are written in terms of U and Y. And this U is function of depth of discharge. Y is also function of depth of discharge, T and TRF. So if you really want to do, you can do it. What we can do, we can fit parameters for u and y. So that is there. So NTGK model is also good. You have to fit the models for u. So u is function of what? Actually, now this is polynomial model as a function of DOD, but this is also very indirect. So later on we'll see the beauty of ECM to avoid all these things. So see, now suppose this u is known to you and u is known. Suppose this constant an and DOD is again, it's a DOD, depth of discharge. So this is dynamic thing. So it will be varying as the time goes on. So T is given temperature. This is reference temperature where these values are we have calculated. Which Bn is also constant. Okay, and this is the definition of DOD. Now, what this NTGK people, actually these are the names of the scientists who have developed this model. So the heat generation source terms. See, the main culprit in unsteady state conduction equation was this. If you know this, then we can solve this conduction equation and we can get T1 and we can get temperature distribution. So this NTGK people, they have given this directly as a function of u, and this is, see, we are solving for this. So we have to solve for this here. So we get 5 plus 5 minus by solving this differential equation. We means here saying it is happening at the back end of ANSYS. We are not solving it. If really somebody want to do, they can do it. So, and this is our standard. So J dot CH, this current density, it is written in terms of Y and U. That means both are coupled. So computational complexity is there. But once you get, now what we have to get here, so if these constants are known to you, an and this exponent, if they are known to, and how many constants are there? 5 and 5. So around 10 constants are there, and this n exponent is there, and also C1 and C2. So if these many constants are available, then your problem is solved. You can solve differential equation, or you can solve this unsteady state heat conduction equation, and you can get temperature T. Again, here also difficulty lies with how much rho we should take, how much Cp we should take, how much K we should take. Okay, so that difficulty is there. Okay, and now this is the interface of NTGK model in ANSYS Fluent. So see, so these many parameters you can plug in, you can run this model, and you can get temperature distribution or dynamics of the battery. So how you can see how the complexity has decreased. So we are going, so this is the equation. So here 25 constants were required to be given, and manufacturer's data is required. This constant will be given by the manufacturer. Then here the complexity is reduced, and this around 7 to 8 to 9 parameters we have to specify. Okay, so we are trying to reduce the complexity by these two models. So first was the classical two-dimensional model. Another was semi-empirical model. That means it is based, some help empirical data is taken to arrive at the constants. This constant A0, A1, A2, like that. Okay. Now the real thing will be doing. Real thing means now we can directly, whatever we are discussing today, you can try at your home. You can try in your laboratory. Okay, so this model, so this is exactly given in documentation of ANSYS. So you'll see ANSYS Fluent documentation. See, so generally what happens, we purchase the battery from market. Okay, we take Panasonic battery. The battery is given to you, and in battery specifications are there with you. And what you do, you assemble the batteries, you prepare your battery pack, and you work on that. And your aim is to anyhow run your vehicle successfully. Okay, so whatever is shown here, it is all is internal to the battery. So it is happening. So this is internal model of the battery. So when we are doing equivalent circle model, you should understand that this is internal model of the battery. It is not that some resistances and capacitance are attached to the battery. So this is internal representation, and we are going to see each and every detail. Okay? So this is battery representation. So this is voltage of the battery. So voltage of the battery, terminal voltage of the battery as a function of time. Terminal voltage of the battery. And what is another thing? So this is I of t, load current. See the beauty of this model.
तो हमें पता है हमें
Deepak sir, I think you are on mute. Karan sir, can you unmute Deepak sir?
झालं का आता?
Yes sir, now you are audible.
Okay. And now we'll discuss this in great detail. Please give me some time. Please give your attention here. I am expecting attention from you because this is really very interesting. Interesting means we can do it. We faculty members working in private engineering college without much effort or without much mathematics, we can develop our own model of ECM's model. I can implement it. And not only that, suppose you are doing hybrid energy storage system involving lithium ion and supercapacitor. So we can work on this and you can publish your paper. Suppose you are working on hydrogen fuel cell. Somebody can think of, okay, there is a hydrogen fuel cell. I can get V of t, I of t as a function of t from hydrogen cell. Let us develop this model. Okay, so you have your own paper. And we don't have to do many things. This MATLAB code is there. You can use the MATLAB code, which is really ready-made available to you. You can work on it. Only thing is that we have to understand it. Okay, and now we are starting that. ठीक है ना? Now how they have done it in this ANSYS. Now here still I am in ANSYS. Now all these resistance. So this is shunt resistance or series resistance. It is expressed as a function of A1, A2 exponential function of SOC. SOC is state of charge. So all these resistances and capacitances and open circuit voltage, they are expressed as function of state of charge because it is actual behavior. And J dot ECH is calculated. So I is current, I of t. So we can immediately calculate it. And Q dot ECH is again. So this is directly here. OCV is function of OCV. OCV is function of SOC. So for each OCV, at each time step, OCV is available. 5 plus 5 minus that differential equation is available, and we can get this. So U is this potential as a function of t. So that data is available if you test your battery at different temperatures. So this plot is this slope is available. So you can multiply with this and you can get Q dot ECH, can put into the differential equation, unsteady state heat conduction equation, and we can get temperature distribution. And same thing is done in ANSYS. So I will directly show you how they are showing in ANSYS. Okay, so this is the interface for all this series resistances and parallel resistance and capacitor resistance. Okay, my point here is that how we can come to this, how we can find out all these constants for our own battery. Okay, and that we will see in great detail. So please give your attention. It may be you may have done it. Okay, so we now deep dive in equivalent circuit model, so that we'll really understand and you can use our for own purpose. So we know that open circuit voltage model. So this is simple model. So we are starting with very simple model. So this is a battery. So we are thinking that this is our battery. This is our battery, and this battery is nothing but a constant voltage battery or infinite source. So this is infinite source where voltage is not changing. Whatever current you are taking from this battery, the voltage is not going to change. For mechanical engineers, you can understand. For example, there is dam. Okay, so whatever. So if you are taking water from a dam, so it is actually infinite storage is there. Okay, if you take one day, For example, you can take 1 day of power extracting from the dam. The level is not changing much. Okay, so this is equivalent to open circuit voltage, but it is not a real case in our battery. Okay, so we'll now deep dive into ECM. We'll try to understand first what is open circuit voltage model. So this is actually a model, and we are going to build on this model. So open circuit voltage model. Open circuit voltage (OCV) is the electrical potential difference between two terminals of a device. So these terminals are there. So you attach a multimeter and you find out voltage of a device when it is disconnected from a circuit and there is no external load. So there is no external load. So if when there is no external load to the battery, and if we take exactly at that moment what is the voltage of the battery, that voltage is open circuit voltage. At that time, it is assumed that battery is in perfect equilibrium. So battery is represented as source where voltage remains constant. So this is the model. Since it is common observation that as the state of charge of battery changes, the voltage of the battery also changes. So this is not common observation. What is common observation? You take current from the battery, its OC will go down. So it is not representing the reality, but this will act as an element into our final model. Okay, so OCV is to be expressed as a function of SOC for better representation of voltage source of the battery. So what is the common observation? Common observation is that you take current from the battery, its open circuit voltage will go down. Okay, so we have to do some modification over here into this model, and now we'll bring dependency of OCV on state of the charge of the battery, and that is also very simple. The dynamics and the mathematics also very simple. And now here we'll see. Now see, this is the observation. This is observation. What is the observation? So this actually this is for charging, and the reverse direction will be discharging. So here over here, so 100% SOC. The battery voltage is around 4.2. Now as SOC is decreasing, what will happen? The OC of the OCV, open circuit voltage of the battery, is going down. Okay, now this is model as, so this is model as mathematically. So I'm reading it. It is common observation that OCV depends on the state of the charge. So done. So from here it is coming from this observation. What is SOC? The state of the charge of a cell to be 100% or 1 when cell is fully charged, and we know it. Changes to the state of charge can be modeled using an ordinary differential equation. So this Z is SOC. So Z later is used for state of the charge. This nu is Coulombic efficiency. And right now, for the moment, we will say, okay, this efficiency 1. Forget about it. Q is the capacity of the battery, and I of t is the instantaneous current. Okay, so I of t is the instantaneous current when this. So we are assuming that this is internal to the battery, and there is load, and this load is taking instantaneous current. Okay, so this is the differential equation, and now it can be discretized because we are solving discretized form of the equations. Okay, so this is continuous equation. So this equation is solution of this differential equation Z of t. Z, that is SOC at t is equal to 0, and normally when the battery is 100% charged, so it will be 1. Then this is capacity, Coulombic efficiency I of t. Okay, and this tau and t taken because this t is, these are the limits of integration, and this we are solving this integration for this. Okay, and now this is discretized. So SOC at time step k is given to you. You are solving for SOC at time step k plus 1 is what? Delta t. For example, your delta t is say 0.5 second. So you can just plug in over here. So you can start from 0. We can start from 100% or 1. So at 0.5 second, we'll what? You can find out how much current pulse we are giving to the battery. And generally, it is assumed that when time step is small, we can regard I of k is constant. So that is the beauty of this. So we don't have to worry much about the profile, because in real life the current profile can be anything. So you can have any arbitrary current profile depending upon the drive cycle. For example, your UDD drive cycle is there. We don't have any control on that. But generally, for initial exercise, we can take constant per current pulses, and later we can convert for the realistic drive cycles. Okay. So this is about SOC, and now we can find out. So this SOC is written as a function of time, and now this OCV is written as a function of SOC. Okay, so what is this? So it is written here, OCV is now function of Z of t. So this is the model. So what happened if you use this model, if you use this differential equation? So what is happening? As SOC decreasing, OCV is decreasing. Okay, and this is common observation. So we are going towards the reality, a real working of the battery. Again, see, this is the model. Another thing. Now this is happening at the, now what is OCV? OC is open circuit voltage. And what is the definition of OCV? When we are discussing OCV, there should not be no load, but our battery is working for the load. So this is actually a static model. Okay, so this is good model, but this is only the static model without any load on the battery. But our why we are designing the battery, because it should take the load. So dynamics of the battery has to be taken into account, and because of that we have to add equivalent series resistance. So this is another level of the model. Okay, so what we have done? So initially there was OCV. Then what we have done? OCV we have written as a function of Z of t. So this is static model. This is idealistic model. So what is happening here? This is most ideal thing. Then this is static model. From static we are adding dynamics. Okay, and this dynamics is added by adding series resistance to the OCV. Now what has happened? Again, this RO is also a function of time. Later on we'll see how we can find out R of t. Okay, so I am now describing the cell's terminal voltage drops below the open circuit voltage when cell is subjected to load, and the terminal voltage rises above the open circuit voltage when the cell being charged. Okay, we know that this phenomena can be explained in part by placing a resistor in series with the control voltage source. The added circuit component represents so-called equivalent circuit resistance, that is ECR. That means this. So this is the dynamics. Okay, so this is what Z of t. Now V of t. So this V of t at the terminals. V of t at the terminals is what? OCV as a function of SOC, which is function of t minus I of t into RO. And it is written in discretized form. Okay, so at time step k plus 1 is equal to, actually the time step. So we'll solve this. We'll put this into this, and we can get V of k at k's time step when Z of k is given and Ik RO is given. For example, suppose so this battery, suppose you are taking say current pulse. So I will show here. So this is I of t. This is t. Suppose this current pulse you are adding. So suppose this is 5 ampere. Okay, and you are doing it for after say 5 minutes. What will happen? So how will be the response? How this voltage will look like? So this is V of t. So this is t. So what will happen? Till 5 minutes, I can show over here only. What will happen here? So there is V of t is not changing. Then suddenly the load is applied. So what will happen? The voltage will go down. Okay, and now after this much time that this current is constant. So what will happen? Voltage will remain at this level. If this load is removed, that means in this time step. So what will happen? Immediately the voltage will go on. And why this change is there? So this is V of t and this is V of t. So this change is because of what? OCV is a function of t. So for this current pulse, what will be the response of the battery? Voltage response. Again, I am drawing it. So for this, the voltage response will be like this. Okay. So these are, if you plug in this point, so this will be as a OCV as a function of Z of t, and this is coming because of this. See, this is capturing the dynamics, but in reality, this is not happening. In reality, we know there is always relaxation. Relaxation phenomenon is there. For example, we are most of we are mechanical engineers, so we know that when this otherwise just forget it. I will go very fast now. See, what is the correct response? The realistic response to the loads. So diffusion voltages. So what is happening exactly? So I have shown that. So when we consider only R of t or series resistance, So what will the response? The response will be like this. Okay. So what I'm saying that you take a battery, okay, you attach load to it. If the response is like this, dotted black lines, then only you can condition only R of t. But it is observed that the response of the battery, response means what? Voltage as a function of time is following this curve. Okay, so we have to take into account this relaxation if we really want a realistic or accurate model of the battery. Okay, so I'm describing here polarization. This phenomenon is called as polarization. Polarization refers to any departure of the cell's terminal voltage away from open circuit voltage due to passage of current through cell. Real cells have more complex behavior. Complex means this. So whatever this is shown, it is called as complex, where voltage polarization slowly develops over the time as current is demanded from the cell. So it is not happening that immediately the voltage is going down. The voltage is going down slowly. So figure 1 illustrates, that means this figure illustrates the voltage is plotted. The cell is at rest for 5 minutes. So cell is rest at 5 minutes. The cell is subjected to a discharge current pulse of constant magnitude at t equal to 5 until t equal to 20 minutes. Okay. So for this time, a current pulse is given to the battery. Then load is removed. Afterwards, load is removed from the battery. And when the load is removed from the battery, so we are getting this response. Again, I am drawing it. So we are getting this response. Now we have to add further electrical elements so that our model is perfect. It is perfectly capturing the dynamics of the battery. And now I will show you how they have done it. Now this is the equivalent circuit model, parallel RC pairs and series resistance model. Now what has happened? So initially OC was constant. We have added dependence on ACV of SOC. Then we have added R of T, series resistance, and now we are adding this parallel RC pair, and such n number of parallel RC pairs will be there. And now we are going to see this in slightly great detail. Okay, so the slow diffusion process of lithium ion cells causes this slowly changing voltage as a diffusion voltage. The realistic model must capture the dynamics accurately. This effect can be approximately closely in circuit using one or more parallel resistor capacitor subcircuit. For example, in figure, combination of R1, C1 perform this function. Okay. So what is V of t? V of t is OCV. We have seen this. Then equivalent series resistance, we have added this. And now here, by adding this R1 and C1 parallel resistance capacitance pair, this is the voltage drop. Okay. So this is continuous equation and this is discrete equation. So this is continuous and this is discrete. And now how this current passing through R1 is governed? So I R1, so I am again drawing here. So this is C1, R1. Current passing through R1 is I R1 and this is I. Okay, I of t. Okay, so the governing differential equation which is representing or which is describing the physics of this R1 C1 pair is very simple equation. This is ordinary differential equation. Now further, this V dot C1 is written as VC1, voltage drop across this RC pair is written as R1, that means this into I R1. So this equation now written like this. So I R1 is R1 C1 d of I R1 dt into or equal to IT. So this is what? This is current pulse. External current we are taking at the terminal. So this is here we are taking I of t. Okay. So if this I of t is known, so we have to capture this. We have to find out this R1 C1 again using parameters. Okay. So what we have to do now? We have to now solve this equation. So this is our ordinary differential equation. Okay. So we are over here. And now we'll see how this equation is solved. Okay, now this equation is represented like this. Okay, x is correspond to I r1 of t. So E of t is I of t. Okay, these are constant. A is constant, B is constant. So what we can do, we can solve this differential equation. So again, I have taken it from book. I will give the name of the book here. So and we can get this solution. Okay, so this is continuous time step solution, and this is discrete time step solution. So in this discrete time step solution, x at case time step, you can write down like this. Okay, so I'm going now slightly faster. Now these constants are plug in, and now see, finally we are getting. So this equation was already available with you. So this is a discrete. So what you can do, if this, so we can start at time step equal to 0. This I of t is given to you. Okay, at different time step at time t. Okay, so this is known to you. This is known to you. Delta t you are choosing. Q is given to you, and we are starting from z. So we can at each time step we can calculate what is the SOC. Okay, using this we can calculate. Suppose initially at time step t is equal to 0, we can get this. I of k is known to you. Okay, suppose R1, C1, I'm assuming here that R1 and C1 are known, but ideally or in realistic way, we have to actually find out using parameter estimation. But here we are assuming that suppose R1 and C1 are given to you for given delta t, we can find out I R1 at k plus 1 time step. You plug in this, you get I R1 at k time step. Okay, R1 is known, R0 is known, and you can find out then V of k. So what we can do, so by solving this equation, we will try to get this. If R1 and R1, C1 and this R0 are known to you. But what we have to do, whether in real battery these are known to you? No, these things are not known to you. What is given? So what we can do, we can find out V of k, we can find out I of k at different time steps. So how the data will look like? So there is time step t, then V of t, then I of t will be there. So 0, say 30 seconds, 60 seconds, like this data will be there. And V of t, we are starting from say 4.2 volt. This will go down. And generally, this is taken as a pulse. So we can take say 5 ampere pulse, then 0, then 5 ampere. So data will look like this. And now using this data, we have to run parameter estimation simulation, and we can get R1 and R2. So that is the main aim. Okay, and that I'm going to show in MATLAB exercise. Okay, so what you have to find out? We have to find out R1, C1, and R0 as a function of SOC. And a very simple example is shown over here. For example, suppose you don't have to do parameter estimation, and this pulse is given to you. Using this pulse, we can deduce how much can be the R1 and C1. So later we can just look at this example through this slide. I will come to know how this R1 and this R0, R1 and C1 are calculated just by using this pulse. Okay, now I will go fast. Now this is the experimental setup for parameter estimation. Parameter estimation means what we have to find out? We have to find out R0, R1, C1 as a function of SOC. Okay, and this is given data. So this data is given to you. So this is voltage data, V of t, and this is I of t. And how we can get this data? We can get this data. Now this is the experimental setup. I'm not going to explain this experimental data because time is very less time is there. So okay, these are just switch. Just by operating this switch electronically, we can get this current pulse. Okay, so this is the current pulse. Okay, and for this current pulse, this is the voltage data, V of t. Now what is our aim here? This is given to you. This is given to you. From where? Now we have battery tester. PCCOE has battery tester. Arbin battery tester is very famous. So we can put our battery. We can adjust the current pulse like this. We can get this. And what we can do? We can get R0, R1, C1, or R1, C1 up to Rn, Cn. Okay. So these values we can get, and we can have our own model, our equivalent circuit model of our own battery, and then we can use that model for battery management system, for thermal management of the battery. Okay, so and so forth. Now I will describe here what is the OCV test procedure, because see OCV is function of SOC. So that first we have to find out what is the this procedure. Soak the fully charged cell at temperature at the test temperature. Again, where we can take this data for different temperatures, 25 degrees Celsius, 30 degrees Celsius, so and so forth. So for given temperature, soak the fully charged battery at least for 2 hours to ensure uniform temperature throughout the cell. Discharge the cell at constant current rate. So this C rate is very small, so as to maintain equilibrium. Okay, until the cell terminal voltage equals to manufacturer specified minimum voltage. Okay, so here minimum voltage is 3 voltage, and they have started from 4.2. Okay, so this is the cycle. Soak the cell at 25 degrees Celsius at least for 2 hours, so and so forth. So what will happen? We'll get, see, this current rate is very small. So ideally, this is operating at no load. Okay, no load means what? Whatever terminal voltage is there, it is approximately equal to OCV. So we can get this. Now we can, using this and this, we can find out the parameters. For example, we can express this as this A1 SOC plus A2 SOC square, like this. So this is polynomial equation describing this, and we can regard this as V or OCV. So this OCV problem is solved. Okay. Another thing. Now, what is the dynamic test procedure? Soak the fully charged cell battery. No, soak the fully. The test procedure is one and the slightly similar. This is discharging. So discharging happening at what? At 1 C rate. See, when we are doing OCV test, the C rate was C by 30 or even smaller than this, because we wanted to maintain no load condition at the terminal. Now here we are maintaining this current condition at the terminal. Okay, and because of that what will happen? We can see this behavior of the battery V of t. Okay, for example, if you see one pulse here, the one pulse will look like this. So if you look at here, so it will be slightly something like this. Okay, at function of t. So this is V of t. Okay, so later we can just look at this. So this is the dynamic test procedure. Okay, and now we are going to see this MATLAB ECM parameter estimation example. Okay, and I have told you that, or we have previously seen that. So these are the parameters which are calculated using such test procedure or such test procedure. For example, see, we can express this as a function of SOC. It can be expressed as a exponential curve, or it can be expressed as a polynomial curve. So that is in our hand, just the exercise of parameter fitting. Okay, and when these values are calculated, EM, here EM is actually, this EM is actually OCV. Okay, and these are time constants. These time constants are what? R1, C1, this R2, C2. Here 3 RC pairs are there in this exercise. Okay, so time is not there, so I will very fast go to the simulation part. Okay, na? So this exercise available online also. Okay, so you just run this simulation. This is very easy. The name of the file is, we can see here, or you can just type this estimate equivalent circuit lithium ion battery data. Okay, so how data will look like? I will open the Excel sheet. So this is the data. So what we have to do? We have to estimate R0, R1, C1, or R2, C2 up to Rn and Cn. So this is the data. This is the data for OCV. Okay, and we can get such sort of data from battery testers, like available in PCCOE or in government engineering college or COEP. So we can get this for our own battery. Similarly, this data is for dynamic test. Okay, so the data looks like this. Now what we can do? So I'm just explaining you what this simulation is doing. And see, this is the battery module is available in MATLAB, so we don't have to write down much code. So this is battery, this is object, battery per sequence. So this battery per sequence is considered as a object. So this object is described, and in this object, so this is the file name. So here, synthetic lipo pulse discharge dot mat. So this file is nothing but this data or data similar to this. So what we can do? Suppose battery tester is there with you and you want to do your own simulation. You just replace this file with the name of the file of your own data. And see, we can convert CSV file can be converted into MAT file. So what you can do, you create this data, CSV format data from your battery tester, give appropriate name, whatever file name you want to give it to you, and add this file name. Okay, so this object is now, see, now this PS object, in this PH object, this data is added. Okay, so this file name. So what this file name is consist of? Time, voltage, current. We can manage it. Load from file. So from this file, this data is added into this object. And now this data is plotted. Okay, now this is what now? This is experimental pulse. This is plot of experimental data. This is current pulse. This is voltage characteristic, and this is SOC. Okay. Now, if you want to see, now this simulation is done for 2 RC pairs. If you want to do for more, so here current threshold is also there. So how much should be the minimum current? How much should be the maximum current? You can play with this. If you want to change number of RC pairs, you can change over it. So what I am saying, if you really want to do, you want to copy it for your own battery, you have to just change this name. If you want to do it for more number of batteries, if you want your model to be perfect, more accurate, you just change it to more number of RC pairs. But more number of RC pairs doesn't guarantee the correctness of the simulation. So I'm keeping it 3 only. Okay. Now what is happening here? What they have done? Let me just explain you what they have done. So I can write over here. So this current pulse is broken. So I'm explaining you what they have done. Okay. So I'm just see, the current pulses are looking like this. Oh, sorry, voltage characteristic. Now what we can do, if we pick up this at various SOCs. So actually this T is what? T is corresponding to SOC. So this SOC, you pick up this value, this value, this value, this value. You means this MATLAB will pick this value, this value, this value, this value, and it will predict what? It will predict, or it will find out the parameters for OCV as a function of SOC. Okay. So what I have explained you are giving this data. What MATLAB will do? MATLAB will pick up this such voltage labels. From this voltage labels, using various optimization algorithms, it will find out OCV as a function of SOC. And same thing is done over here. Okay. And here appropriate number of RC pairs are calculated. Okay, time constants are calculated. See here, initially when simulation is starting, what MATLAB has done? So initially all time constants are 0. All these values are 0. And what this MATLAB has done? MATLAB code has calculated SOC as a function of time and R0 as a function of time. How R0 as a function of time is calculated? Okay, so R0 as a function of time is calculated. For example, see, if you look at this pulse, so there is some region here. Pardon me because my figure is not very good, so I will just draw something like this. So when this relaxation is happening, so there is some portion which is immediately returning to the some voltage level, and using such voltage levels, R0 is calculated using parameter estimation. Okay. Okay, na? So using such levels, so this and such point, using such point, this point, and using such points where voltage is immediately returning to the some higher value after removing the load. Using such values, we can calculate R naught. Okay, so same thing is done by MATLAB over here. See, so initially EM, that is SOC, is calculated as a function of SOC, and R naught is calculated as a function of SOC, and these time constants are 0. Now the time constants are calculated. Now how time constants are calculated? You can just look at here. We have seen this exercise here. So for calculation of time constant, MATLAB will come at this point. It will come at this point. Again, it is implemented in the code. And since more number of pairs are there, there can be some relationship. Okay. So the time constant for one constant pair is what? 4R1 C1. Okay. So these time constants are calculated. So what this MATLAB is doing? See here. So this time constants are calculated. Why time constants are calculated? Because time constant is required. If you know R1, you want to calculate C1. To calculate C1 from R1, you require time constant. Okay. So this is going in a very systematic way. See, look. First, they have calculated. MATLAB has calculated SOC, OCV as a function of SOC. Then R naught as a function of SOC. Then using pulse data, MATLAB has calculated time constants. These time constants for 3 RC pairs. And now the real thing will start. This is a really beautiful. I will show you what optimization algorithm is used over here. Huh? Okay. So all these things are given. Okay. So finally, what this MATLAB will do using this T1, this tau1, tau2, tau 2, tau 3, MATLAB will calculate R1, R2, and R3. And what solver is used? Linear least square non-linear optimization. Okay. So it will calculate these parameters and give us these parameters. So finally, what is available with us? OCV as a function of SOC, R naught as a function of SOC, R1, R2, R3 as a function of SOC. And once these are known to us, what we can do? So these red lines are the real data, experimental data. And by using our parameters, that means EM, R naught, R1, R2, R3. Now this simulation data is plotted along with the experimental data. That means what is happening? See the beauty of this. Now we have a model of the battery which we can use for battery management purpose. We know the full dynamics of the battery only by using R naught, R1, C1, R2, C2, R3, C3, and OCV. Okay. And see, now the very last point I want to show here is that it looks very difficult. But if you look at this linear square, non-linear, this LSQ, non-linear. So from where they are taken. So if you see the implementation of this, so we have done this in optimization. Many of us have done optimization course. It is not opening. Okay, forget it. It is not opening. So my point here is that, see, we have done optimization course. These parameters are calculated using optimization methods. But these optimization methods which are used in this course, they are also not very great. So you must have heard about this stochastic SGD. Stochastic gradient descent. Or you must be knowing this Newton methods, gradient based methods, or Marquardt method. I will show you this Marquardt method. My point here is that, see, all these methods we have studied, and the MATLAB has implemented this model to predict the parameters. So my point is that if somebody don't want to use MATLAB, he or she want to show that, okay, I have done something nice work without using MATLAB. So without using MATLAB, use Python or any other code, develop the battery model and publish your own paper. Not only for lithium-ion battery, you can do it same for even fuel cell. You can do it for hybrid energy storage systems like lithium-ion battery and supercapacitor. So I'm giving hint how we can publish the papers, because somebody might have done it in MATLAB, we can develop our own code. Okay, so I am showing you here. See, so this non-linear least square method. So they have probably used MATLAB. They are using internally this method, markbat method. Okay, this is very simple method. See, my point here is that it looks very difficult how they might have done it, but if you look at the basics are very simple. Okay, so this is the basic, either Newton method, then some modification of Newton method, we get markbat method, and further what I can say, further modification will give us BJFS method, okay, or Shannon method. So my point here is that, see, if you really want to something contributory, if you really want to do something from fundamental point of view, and also experiments are there with us, experimental setups are there, we can generate our own data, and it will be a really good contribution, and we can publish the papers. Okay, so so this is about the equivalent circuit modeling. And finally, I want to say, see, you must have done this this models earlier also. You must have seen this. My point here is that, see, when we are doing electrical vehicles are very old. It is not new technology, but challenges are new. Okay, so we don't have to, we cannot forget fundamentals, because when fundamentals are there, then we can find out the optimized solutions. When optimized solutions are there, then there will be improvement, and when improvement is there, then new things will come out. Otherwise, what will happen? You know technology. Yes, it is very good that we should every day, or somebody from industry should come. They should teach us what is happening in the industry. But we as a teachers, we as an academician, we must assist industry by working at fundamental level. Otherwise, what will happen? Actually, say, I work in industry and I know how industry works. They generally don't look at, generally, I'm not saying that this is not a blanket statement. Generally, they are so busy. There are so many challenges are in front of them. They don't have time to look at the differential equation. So my point here, I'm appealing to all the participants that if you really want to work in electric vehicles or any new field, don't forget the fundamentals. Look at the differential equation. Try to see what is happening at the back end of the softwares. You might be using softwares. You might have developed. You might have published many papers, but look at the fundamentals. Okay, so this is about my lecture or my delivery. Thank you. Now you can ask me the questions, sir, if at all you have any question.
So if any attendee is having any question, you can unmute and you can ask. Kolikar sir, I think you have asked one question, so you can unmute and you can interact. Sir, there is one question in chat box. Should I read it for you?
Please read it.
So this question is on in MATLAB, how to model this EV with the specific values of SOC and other design values.
Yes, very nice parameter. Very nice question. See, we don't have to do much thing, because see, this model is already implemented. You get this data. So my Excel sheet is visible to you. Hello.
Yes, sir, it is visible.
Okay, so you get this data. So data point 1, you get, and see, we are not going to do it manually. For example, if you are in this PCCOE, PCCOE has a battery tester with them. You put your battery there, you put your cell there, and you get this data. Convert this CSV file into MATLAB file, and you bring this MATLAB file over here. See, this is so this file name. Okay. So you create this data experimentally, and probably this battery testers, they are giving data in CSV format. So convert the CSV into MATLAB format. You bring this file here. Okay, you have brought your data into MATLAB and just run this simulation. Okay, so I hope I have given the answer of your question.
Thanks so much.
The next question we are having from Vagulikar sir. He is asking, this DOD or D of D itself dependent on many operating parameters. So is this true?
Yes, it is. See, SOC itself can be function of many things. Okay, it can be function of temperature. It can be function of many other parameters also. But here, OCB and everything, all these parameters, all these resistances and capacitances, at least in ECM, they are expressed as a function of SOC or DOD. Okay, so we have to just look at the SOC or DOD, because otherwise what will happen? Again, we are deep dive into the SOC, which depends on other things like diffusivity of these particles. Again, then we are moving towards this micro scale models. And here we are not. So this ECM is macro scale model. It is at battery scale. We are not seeing what is happening inside the battery. Okay. Again, for example, see, we are not looking what is happening here. We are not. So we are looking at outside. And outside what? So SOC. We know that SOC this OC is function of SOC. We are just looking at SOC. Now this SOC can be function of temperature. It can be function of any other parameters, like it can be function of this sigma plus, sigma minus. Okay, we are not looking at that. This SOC can be function of the particle size. This SOC can be function of particle distribution. We are not looking at. And when I'm saying the SOC, so this is one my DOD is 1 minus SOC. Okay, so I have answered the question.
Sir, is the MATLAB version is free of cost?
Yes, I would see. I would actually, if you have MATLAB with you, I'm using this online thing, because this license is available in our college. So I've logged on to online thing, and I just again, this is very simple. You just see online and just copy it. खूप जास्त काय करायचं नाही. It is very simple. माझा एक PhD चा विद्यार्थी याच्यावर काम करतो.
Hello.
Okay. Hello.
Hello. How we can overcome the fast charging problem in batteries while using the solar energy, by keeping the solar energy in the electrical vehicles? It might be reducing the problem of fast charging and maybe overcome, sir.
See the battery characteristic and battery dynamics. So it is very strong function of C rate. Okay, so you control the C rate, and then see, we are looking at C rate. So control C rate, you are controlling dynamics of the battery. Then C rate, how much C rate you want from solar panel? It is up to you. It is up to your electronics. So you have good electronics, then you can take care of that. Okay. So if your power electronics circuit, your power electronics and control is good, then you can take care of all those things, charging, discharging.
Means here we are bothering about the battery charging, fast charging, and it might be when we are keeping the panels according to our electrical.
No, see, sir, what is happening? Suppose the battery, you are getting battery from a manufacturer, for example, Panasonic. Okay, so Panasonic is saying that you can charge your battery at 10C. So we cannot go beyond 10C. No? So if you go beyond 10C, what will happen? There will be disintegration of the particles, and all this entropic things will come into picture. Heating will be there, and you are damaging the battery. Okay, so that is my point. Once the battery is given to you and the C rate is given to you, then how we cannot go beyond whatever maximum C rate is there. So that question is out of that is out of question. A battery of 10C is given to you, and you are saying, okay, I will charge it at 20C. You cannot do it. You are destroying your battery. So that limitation is there. Again, then the question will come, at what higher C rate I can charge my battery. Again, you can ask your manufacturer, give me a higher C rate battery. Artificially, you can't do anything. Na? Am I right? Or have I answered your question?
Yes, sir. But so many things it will be there. If we are keeping the battery charging, the driver who is driving the vehicle, he may going to be in a another mode. How much time it will be going to be charge the battery?
So let me draw a figure over here. So I will draw a figure for you. See what I'm saying. So this is your battery. Okay. We are getting, so we are, for charging, we are moving current in the battery. So what manufacturer is saying, so you can charge battery at 10C. You can charge at battery 20C. So you cannot charge your battery beyond this. That means you cannot charge this battery at 30C. Otherwise, what will happen? You are destroying your battery. That means you are reducing the life of the battery, or even you are reducing the capacity of the battery. That you cannot do. Okay, now you are saying that okay, I can load the I can give load to I can load the equipment to the battery. Again, what is the maximum? Suppose manufacturing is saying that okay, 20C, you can get current corresponding to 20C. So that 20C is there, but how this 20C will come? That is on your controlling thing. So my battery can give 20C, but how you can use 20C? It is up to you. Again, suppose your drive cycle is like this. Such a complicated drive cycle is there. Okay, so this is velocity as a function of time. And if your drive cycle and some torque is there, your torque in drive cycle is demanding this 20C. You have to give it 20C. You know? There is no any compromise on it. So many things are happening there. I have avoided all these things. What I am saying here in this discussion, we are discussing only things: how we can model this battery, how we can represent this battery. Again, why this representation is required? Because once we have this V of t, you know, we can predict. So what will be the V of t after 20 minutes or after 1 hour or after 10 hours? If you use this drive cycle consistently.
Yes.
And not only that, so you can simplify this. For example, say in this model, the beauty of this model is, see, for example, I want to find out temperature rise. Up to say 90% accuracy, or again 80% accuracy. I don't know 100%. So what I can do, as a first principle, I will just say I square R1, I square R2, I square R0. So this is my heat loss from the battery. And I can then find out temperature on the basis of this. I can measure, I can predict the temperature on the basis of this. Then in reality, what will happen? We'll carry out the experimentation. We'll find out what is the actual temperature. If it is giving us 90% accuracy, we'll say, okay, this model is sufficient for me. Okay. And depending on that, then on the basis of this, we can design our cooling system. But we know that we are working at 80% accuracy. We are working at 90% accuracy. So we cannot guarantee, I cannot say that whatever model I have developed, it will give me 100% accuracy. No, it is not possible, because after all, this is a model. Even P2D, it is also a model. Not only that, this governing differential equation itself is a model. We don't know. See, for example, if somebody is challenging, okay, I don't know this model, I want to use this model, fundamental principles. But whatever this rho, Cp, sigma plus, sigma minus given by the manufacturers, they have given these values by experimenting, by experimental things. So this is also in a way a model. So this will also give you, it will not give 100% accuracy. Your predictions will not be 100%. It will say 99%. Again, it depends upon how you are simulating the things, how you are modeling the things. So some sort of uncertainty will be always there, but that uncertainty should not be 50% or 60%. Uncertainty can be say 5%, 10%, and we should know it. For example, you have designed the system at 90% accuracy or 90% reliability. You should know it, that my systems are designed for 90% reliability, and I have to take so much of precaution that I have to then play in that margin of 10%. Otherwise, your battery will go to thermal runaway. That we have to avoid. Okay.
Hello. Hello. Dr. Abhijit again. Sir, any UDF while solving the problem in the ANSYS Fluent, have you used any UDF?
Actually, see, in ANSYS Fluent now, everything is implemented as this user-defined functions. So my experience here is that, see, everything is good. So the differential equation, these solvers are good. Ultimately, it boils down to your machine.
Hello, sir. Myself, Dr. Manish.
Yes.
Working as system professional at Jaipur. Sir, as you shown, there are various reasons for the thermal like joule heating
Hmm.
and electrochemical heat generation at the electrodes.
See,
And-
I have written here, for example, see these terms again from fundamental point of. So these are what? So this is joule heating,
Yes,
then
sir.
electrochemical, then
Yes.
short circuit and thermal amuse.
Yes, sir. So which is playing major role?
See, in normal routing, this short circuit and abuse, we have to avoid it. No? So if you are not good designer,
Short circuit, so short circuit is like some mishandling. But suppose
Hmm.
these are inherent characteristics. Joule
so
heating.
see, we cannot avoid this now. We cannot avoid this I square R rating because we are taking current, we are getting current from the battery. And
Yeah.
also we cannot avoid this electrochemical heat generation because of electrical chemical reaction, the electrons are coming out and those electrons are nothing but the current. So this is inevitable. So these two source terms, we cannot get rid of this because otherwise the battery will not work. No? We can, but we cannot.
I want was is there are you trying to reduce this effect? Have you tried to reduce this heating effect? We cannot eliminate fully, but we can reduce to some extent. Can we reduce to some
Say,
extent?
we may say when a battery is given to you, we cannot do anything. But you are working on the battery material. You are doing battery material characterization. You are developing new battery. Then we can have appropriate value of this. This is everything in your hand now. Then you can reduce this. But once the battery is given to you, then we cannot. Say these constants are given to you. No? For example, you look at this 5 plus and 5 minus. So these are fairly standard values for lithium ion battery. You are taking so whatever current you are getting from the battery, you are loading it now, so you cannot avoid it. For example, electrochemical reaction, for that much electrochemical reaction, that much heat source will be there now. So we cannot, once the battery is given to you, we can't do anything with this. So what we can do is we can design a good cooling systems. That is only in our hand, or our prediction of temperature should be nice. And when our temperature dissipation and temperature will be good, when we solve this equation perfectly, or if the knowledge of this rho Cp all are in our control.
Thank you, sir.
I have one question.
Hmm.
Sir, in MATLAB, we are having all the three models, but if we are changing those values, that won't be running because there. What can we do, sir? We want to simulate everything that will be a previous models.
Actually, you are not audible. Huh?
Sir,
I'm not able to listen you properly. So can you type your question, then madam can read
sure,
question?
sir. Yes, sir. I will type it in the chat box.
So, madam, we'll go with the next.
Yes, sir. Sir, there is one question in chat box. Which
Yeah, we will
energy
have this as the
storage
last question.
technology is best suited for rapid energy discharge and regenerative braking?
So actually, I'm working on the supercapacitor. So supercapacitor plus lithium ion. What can if you want higher acceleration, higher charging, you can your supercapacitor will charge or discharge fast, and this other conditions will be taken care of by lithium ion. So hybrid storage systems, we should work supercapacitor plus Li batteries. And people are working. People have worked on it. You can have a number of papers on supercapacitor plus lithium-ion battery. And we know that the supercapacitors are for higher for fast charging and discharging. And if you want higher acceleration, higher acceleration particularly, your supercapacitor will can work like a flywheel, because if you are from mechanical, you can understand how flywheel works. So immediately it will discharge. Then static conditions or uniform loading condition will be taken care of by lithium-ion batteries. So this is good combination, supercapacitor plus lithium-ion. Other than that, I don't think, because in electrical, what we have with us, we have a resistance, then we have capacitor, and there is no inductor. What we can do with inductance? No? So if we consider electrical components also, we can have only capacitor along with this electron source. So this is also electron source, but it is storing it.
Sir, in MATLAB, there are pre-models, but if we try to change the values, it gives errors. So what is your suggestion over this?
See, again, so that's a very good question. You try to understand each and every model from a fundamental point of view. For example, I have told you that, okay, I will show you this. suppose you are working with this, you should try to understand what exactly is happening when parameters are being estimated. And you can see, initially you can start with, initially suppose you want to copy this, you want to do the same simulation without touching it. What you can do, you can just change this file, see what is happening. Then what you can do here, you can change number of RCPs. Then what you can do, you can take different solver. Now what is the solver over here? This. So like this, you can play with this and you can try to get more insight. No? So that is the only solution. And you should know what exactly is happening. You should know the dynamics. Otherwise, what will happen? You take any fluent example. For example, you can take this. The sol thing is available. Demonstrative example is available in Fluent. You change something, you will go into trouble. Why you go into trouble? For example, if you want to use a Newman P2D model, there is no problem with calculations. The model is perfect. You are not changing the parameters. What is happening generally in Fluent? Whatever meshing you are taking, there is problem at the mesh level. Similarly, now we are talking about MATLAB. So in MATLAB, what we are doing? These things. You should try to understand what is the meaning of each and everything like this. For example, this is object. In this object, this is the function. And this function is taking these parameters. This parameter pair, this and this. So update ending false. So what is the meaning of this? We try to get its meaning from MATLAB manual. That is the only solution. And in addition to, you should know what exactly is equivalent circuit model. Okay, na?
So I think all the questions have been answered by Deepak sir. So on behalf of PCCOE Pune, I extend my heartfelt thanks to Deepak sir for delivering such an insightful session on thermal issues in lithium-ion batteries, the associated physics, chemistry, and mathematics, the basics of MSMD modeling, and Newman's P2D model, NTGK model, ECM model. So your extensive expertise and depth of knowledge shared during this session have provided us with a comprehensive understanding of many critical aspects which are related to battery technology. And your ability to simplify the complex topic and relate it with the practical application has greatly enriched the learning experience of attendees. So we truly grateful for your time, effort, and knowledge. Thank you once again, Deepak sir, for your contribution to this ATAL FDP. We thank you from bottom of our